So without further ado, Sechen, take it away for the first paper.
Thank you so much. Hi everyone. Today I'm going to present the paper, Understanding Leakage in Searchable Encryption, a Quantitative Approach. This is a joint work with Sasha, who is here, and also Bogdan. So this work is a very theoretical work, but I hope I will keep it high level so that you won't fall asleep in the middle. So let's start with a quick introduction to searchable encryption, because I believe that not all of you know about this topic. So in searchable encryption, we consider two parties. There's a client and there's a server. The server is honest but curious in most of the settings. The client holds a set of documents. These documents, you can think of them as a set of emails and so on. Usually what happens is that the client is going to index this set of documents so that the client can search over the documents. But you don't want to just store that locally because that costs storage on the client. So instead, we want to have a mechanism to allow the client to outsource that inverted index to the server in an encrypted form, of course. So after doing all of that, the functionality we try to achieve is the following. The client is going to generate some kind of query with some kind of keyword in this case. This is going to be encrypted, sent to the server. The server does some kind of computation, and by the end of the computation, the server is supposed to return the documents that match the query. But in the simplified case, we don't consider the document retrieval, but only the index retrieval, meaning that by the end of the query, the client only gets the document identifiers of the documents, but not actually the document content. That's sufficient for this talk. So of course, this is a privacy, for this kind of protocol, privacy is important. In this case, we care about the privacy of the actual data and the queries themselves. Okay, so privacy is important, so definitely we have a security notion for that, right? So we have a standard security notion for that, and it was proposed in 2006. So it has been almost 20 years for this security notion. So to give you a kind of high-level introduction to what this security notion is, it's simulation-based games. So there are actually just two games. There's one real game, and in the real game, it's a real execution of the scheme where there are two parties. One party is the game itself. The game acts as the client, and here the client has secrets. And then the other party is the adversary, and the adversary plays the server. So you can imagine that in this interaction, the server is going to observe the transcript of the whole execution, right? Then we have another game, that's the ideal game. And in the ideal game, it's a simulated execution of the scheme. And by simulation, I mean that the adversary doesn't really interact with the scheme itself, but it interacts with a simulator that has access to the leakage of the real data and the queries. Okay, and the server and the client plays the same roles as before. And crucially, if you can prove that the real game and the ideal game are indistinguishable, then we have the standard security. And intuitively, what that means is that if the attacker, the adversary in this case, cannot distinguish the two games, then the adversary cannot learn more than what the leakage entails. So that's pretty much it about the standard security notion. And if you are curious how it looks like, concretely, it looks like something like this. You have a real game on the left, you have ideal game on the right, and they are computationally indistinguishable if you can prove the security. If you follow none of that, at least one thing you should remember is that security is quantified by the leakage function. As soon as you show that you have this leakage function and the two words are indistinguishable, you have security. I will say that if everything really works out, then that's the end of the talk, nothing more to discuss here. But unfortunately, that's not the case. And there's a lot of problems with the standard security notion. So let's dive right into that. So there are mainly two issues with the standard security notion. The first is that leakage functions I've just described to you is often very, very complex. Maybe you have a background in MPC, and you know that there you may use a very similar kind of security definition, and there the leakage function may just be something very naive. It can be just bought, meaning that there's nothing is leaked, or it can be the size of sets in a PSI protocol, right? So that's very naive, but let's see what you can get in searchable encryption schemes. It's something that's pages long, and it's very hard to decipher what that means. So, okay, if you have leakage functions, they are long, what does that mean? Probably you still have a security proof, so maybe everything is secure, but unfortunately that's not the case. These leakage functions can really be exploited, and they have been exploited time and time again. And if you want an example of that, look no further than the next talk. Right? If that's not enough for you, then here's a list of 10 more attacks. And these attacks don't only apply to one scheme, two schemes, they actually apply to thousands of searchable encryption schemes. And that's where the problem is at. So in summary, what I've told you so far is that a security proof in the standard security notion, in the standard security model for searchable encryption, does not imply privacy of data or queries. And that's the problem. So now, knowing that, there are really just two options, right? One option is that we are just going to accept the fact and design schemes that actually with very little leakage, and you can say, yes, these schemes are secure. But this is not very easy. So here is an example of a scheme that has very small leakage. I want you to pay attention to the third row and the last column and the third last column. There, the numbers you see are the communication costs of a standard encrypted multi-map, which is kind of searchable encryption scheme with a lot of leakage, and then a scheme with minimal leakage. What you see there is that the communication overhead by using a scheme that has very little leakage, which is the third last column, is really, really high. Here it's 180 times, so you don't want to, it's very hard to get a scheme with small leakage. Right, so we really need the alternative approach, which is we design schemes that are efficient, but with some kind of leakage. Then we try to argue that that leakage is harmless, or at least it doesn't lead to devastating attacks. So there's been a few attempts at this, quite a few, in fact, and they can be categorized into a few categories. But in the interest of the time, I'm not going to go through all of them. But you are welcome to read all of them on your own. So let's quickly go through what we have done in the paper on a very high level. So our work is actually inspired by one of the previous works on quantitative information flow. And what we have here is a very similar approach. So our security is going to be quantified by a leakage function. And the leakage function looks something like this. It has 4 components. The first component is the function itself. It's a functional description, right? So, and this description is known to the adversary. Then the second component, the W, is actually a guess made by the adversary. And the goal of the adversary is actually to maximize this function, right? So, and the last 2 components in this case are information known by the game. DB here refers to the database itself, and the Q with the arrow on top refers to the set of queries. As an example of quantitative information, a leakage function, we have a function that is 1 if the guess is equal to the database and 0 otherwise. And this captures the class of attacks that corresponding to database reconstruction attacks. So we can use this function to capture a lot of different classes of attacks. But I don't actually have the time to describe to you how we actually use this function to construct our security notion. But instead, I will just give you a comparison of what can be achieved with the standard security notion and our security notion. So we'll have a few criteria. So the first one of those is what do you quantify the security notions over? In the standard security notion, it's quantified over the leakage function. And in our notion, it's quantified over the quantitative leakage function. Although both sounds like functions, they are actually very different. Okay, so here the goal for the adversary in the standard security notion is just to distinguish the real game from the ideal game. Nothing more than that. But in our security notion, we only have 1 security game. There's no 2 games. And in that game, the goal of the adversary is to maximize the quantitative leakage function. Finally, one more, there are two more things. One difference is that in the standard security notion, the output of the game is just a bit. In our case, it's a real number. And finally, the security guarantee of the standard security notion is nothing because we don't know what that leakage translates to. But in our case, we can actually show that if the output is small enough, then we can show that the scheme is secure against a class of tags. With that, I'm not going to show this. With that, it comes to the end of the talk. If you are interested, you can scan the QR code to read the paper. Thank you.
Thank you for the talk. So questions? Great.
Thank you. Oh, thank you very much for the talk. Very nice. So your quantitative leakage function, is it like the G vulnerability from Quiff, or is it?
Yes, it's very similar, but slightly different because in the G leakage, if you remember, you have a source, you have an output. You only have two quantities, but in our case, you have more than just two quantities. If you look at this slide, you see the guess itself, you see the database as a component, you see the queries as a component. So the guess has more freedom in some sense.
Okay, so it doesn't really, this does not really play the role of a channel, right? The database and the queue?
It's similar to a channel, but in this case, it's more complicated. Because in a standard channel, you usually just model the input and output as random variables, and that's it. But in our case, there's a lot more going on because you are running a scheme on top of these random variables in some sense.
Lovely, nice, yeah. Brilliant. Thank you very much.
Thank you.
Do you have any more questions? Up there?
This might be a bit of a dumb question, but do these new defined security notions have any correlation with forward and backward privacy, so to say, in searchable encryption?
Yeah, thank you for your question. Well, in this case, we don't actually consider forward and backward security specifically, but they actually can capture those attacks with the leakage function, quantitative leakage functions themselves, right? Because you can say that, okay, so for example, you know how that works, so I don't need to explain that.
We would have time for one more really quick question. Okay, and let me ask one. For whom is this defining the leakage function made? Because I think a cryptographer can properly do that, but if you give the real number to a developer, that might not be that useful either, right?
Yeah, thank you very much for the question. We actually have a whole section discussing how to pick all these things in our paper. So really, this is not a job for the developers, it's a job for us.
Okay, good.
Yeah.
Thank you.
Thank you.
Okay, then the second speaker. And thank the speaker.